This lesson is on comparing the infinite as we begin our more in-depth study of infinity. The first lesson hopefully was not too difficult, and it established what a one-to-one correspondence is. Now I imagine you know what the vocabulary is for a lot of the things we're going to study, such as what a finite set is, or if a group of objects is finite. Without using strong mathematical language, you simply could say a finite set has elements in it that if you had the time, you could count. Now, a finite set could be something that just has one or two members in it, even no members in it. It could have 1,000 members in it. It could have 6 vigintillion members in it. Now that is a really large number. It's a 1 followed by 64 zeros. And it's not something that you would actually want to count, but it would be finite because it is countable. So one easy definition of finite is a set that is countable. Compare that to an infinite set. That means it has a number of elements in it that is not countable. You could actually keep going. If you work past 6 vigintillion, you would say, well, it continues even beyond that. You can always find another one in the set. Now, one-to-one correspondence, hopefully that has been established, that if you pair up one element from one set with another element from another set, and they only are paired together, not with anything else, and if you have the same number in each set, then we'd say that there's a one-to-one correspondence or a one-to-one relationship. It's spelled in various ways and abbreviated like this, but it all means the same thing. Now, if we're actually going to try and compare the infinite, well, that's a little bit difficult. How do we compare one infinity to the other? Would it be possible that one infinity could actually be larger than another infinity? That seems strange. But one way to put it into a comparison that makes sense to us is, what if we had an infinite-sized marble container, and we filled it with an infinite number of marbles, and we had 2 of these side by side? Well, how would we know that they're the same size? Well, we could go in and take one marble from the one and one from the other and do a one-to-one correspondence like this. Keep pairing one from each set together. And we could do that, and then we could continue on our children and our grandchildren and great-great-grandchildren. Well, with an infinite kind of thing, we wouldn't be able to actually get to the end, even if our great-great-great-great-great-great-great-grandchildren did it, everybody from now till then. But that is one way to compare it. In working with this, it's difficult to just simply say, okay, now let's look at infinity, and what size is infinity? Well, because we can't say what size it is, we have developed a term in math called cardinality. It's referring to the size of a set, and it doesn't necessarily have to refer to the number of elements in the set. Now it can. With a finite set, if you had a set of the months of the year, you could say, well, it has a size of 12, a cardinality of 12. But with infinite sets, you really can't do this. After all, how do you say what the size of the natural numbers are? It's an infinite set. So if we want to talk about cardinality, then we need the one-to-one correspondence that we've been working on. The one-to-one pairing, if you can establish that and prove it, that means the 2 sets have the same cardinality. Now, if you're going through these infinite-sized marbles containers, pulling out marble and doing a one-to-one pairing or a one-to-one correspondence, suppose one of them didn't have an infinite number in. Eventually we would get there and the barrel would be empty, and the other barrel still has something in it. Now, probably at some point you lost count, or your children lost count, or your great-grandchildren lost count. So we don't necessarily say, oh, the one set had 64 vigintillion marbles in it. You could say, well, there's not a one-to-one pairing with this, and so the container that has marbles in it yet has a greater cardinality than the other one, and everyone would know that it means there's more marbles in that one than the smaller one. Now, in looking with cardinality, is there a set with a cardinality greater than the natural numbers? Now, the natural numbers is infinite in size, right? We can continue counting, and our children and great-grandchildren and never come to the end. Just keep going. We could use supercomputers to do it real fast, but they would have to run an infinite amount of time as well. Now, to do this, we need to have some way of comparing infinities that we know that there's a one-to-one correspondence to show that they're the same size. If there's a one-to-one correspondence, it's the same size. So to introduce the notation we're going to use, I'm going to compare the natural numbers with the natural numbers. Well, that seems kind of strange, but hopefully we just see that yes, we know that they're going to have the same cardinality. After all, it's the same set compared with itself. And so when we do this, what we can do is set up an n equals and then use parentheses to represent whatever is inside of the set, in this case the naturals, and we list all the members. Well, we really can't list all of the members, so we use an abbreviation like this. The naturals have 1, 2, 3, 4, 5. The ... means that pattern continues. In fact, it continues until you get to n, whatever it is, whichever one that is that you're working with, and even after n, it continues on. Now, if we wanted to compare the cardinality, then we show a one-to-one correspondence, and graphically we can show that by using arrows that have double arrows, one on each end. And this means that we're going to pair 1 with 1. Now we're going to pair 2 with 2, 3 with 3, 4 with 4, 5 with 5. This first part establishes the pattern, so everyone can see it and say, okay, I know what you're doing. The second part gives the definition and says, now whatever marble it is, call it n, from the top naturals, I'm going to pair it with that same number n on the bottom. And that establishes the one-to-one correspondence. In the beginning, first 5 there shows the pattern, and it's defined by the second one. So this is a good way to do your homework to show how these pairings work. Now, let's compare the naturals with the whole numbers. Would the whole numbers have a greater cardinality? After all, if we look at the whole numbers, oh wow, it's all of the natural numbers plus 0. Well, wouldn't that mean that there's one more element in the wholes than there are the naturals? If we look at the pairing that we had and simply put 0 in the beginning of this, wow, that would give the idea that, wow, maybe the whole numbers has a greater cardinality, that it could actually be larger than the natural numbers. But, just because we don't get a one-to-one pairing the first time that we do it, doesn't mean that we can't. So let's try another way. Let's shift this down. Let's set up an n out here, and the natural numbers on the top and on the bottom, and say, well, what if we just paired 1 with 0, and then 2 with 1, and 3 with 2, and 4 with 3? So we realize that from the naturals, like we take 5, and we subtract 1 from that to get 4, and pair that with the whole number that is there. 6 minus 1, pair 6 with 5. Well, if we're doing that kind of thing, then we would take n and pair it with, no, it's not going to be paired with n because we're subtracting 1 from it. So what we need to do is to change that and say that it's going to be n is paired with n minus 1. Now we've established the pattern and defined it, that the pattern is any natural number is paired with a value 1 less to it in the whole numbers, and then that means that they actually have the same cardinality. So this is true. The whole numbers, even though we maybe at first thought there was 1 more in it, infinity is so big you can add 1 to it and it's still infinite. So they have the same cardinality. Now, we added a number, in this case 0, and found that it had the same cardinality. Well, what if we took a subset of the natural numbers? What if we took just the multiples of 10? Well, n would still have all of the natural numbers in it, and the multiples of 10, if we ignore 0, since that's just what we're going to do, and start with, well, then the first one would be 10, and then 20, 30, 40, 50, 60. So we look at it and say, wow, we could kind of set up 1 and 10, but then there's 2, 3, 4, 5, 6, 7, 8. And then if we want to pair 20 with 20, it's a problem. Oh, they've got for every 10 elements in n, you have to pair it with just one multiple of 10. However, if we write it this way, we see that maybe it is possible to do. If we paired up 1 with 10, and 2 with 20, and 3 with 30, and of course 4 with 40. So for every n, we multiply it by 10 to get its pair of 50. So 6 times 10 would be paired with 60. So if we're going to do this, then we need to establish the relationship and change the n to say that it's 10n. Take n and multiply it by 10. So we say, yes, actually, wow. Even though we think of this as we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then 11, and that's paired with a number, and then you have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, even though it seems like there's a lot more in the naturals, we actually find because they're infinite, they have the same cardinality. They are the same size as we think of in non-mathematical terms, but they are the same. They have the same level of infinity, the same cardinality. There are as many natural numbers as there are multiples of 10. Now, what if we compare it to the integers? Kind of remember the integers are like taking the whole numbers and also making the negatives of each of these. Now, if we start pairing 1 like we did with the whole numbers, 1 with 0, and 2 with 1, and 3 with 2, well, then we use up the entire natural numbers, that infinity of natural numbers, just on the positive infinity on the right-hand side of the integers, and we have an entire other infinity that is not covered in the one-to-one relationship. Could that mean that there are more integers than there are natural numbers? That you have an infinity, and then there's another infinity, namely of the integers, that is greater, that is, quote, bigger than the naturals. That would imply 2 levels of infinity. So the integers appears to be like 2 levels, having 2 infinities in it. Wow. Well, maybe we should try and do a one-to-one correspondence. Now we can play with this for a while. And when you read the book, they give a suggestion that what you can do to find a one-to-one correspondence is to pair 1 with 0. We've got to start someplace after all, right? Now for 2, pair that with -1. And then 3, pair that with +1. You know, we started with 0, then we went to the negative direction. We don't want to forget the positive direction, so we paired 3 with that. And we don't want to, again, forget the negative direction, so let's pair 4 with 2. And let's alternate like that. So if we pair 5 with 2, then we go back to the negative and pair 6 with -3. Go back to the positive and pair 7 with 3. And we realize, wow, you know, all of the even numbers with the blue arrows are paired with the next negative number. And all of the odd numbers we pair with the next positive number. So as we keep going, we realize, wow, one infinity actually satisfies 2 infinities. 2 infinities fit inside of 1 infinity. The infinity of the integers is the same cardinality as the natural numbers are. So even though it appeared like it was twice as big, infinity is so big that it can absorb another whole infinite number of numbers inside of it and still be the same size, the same cardinality. Kind of surprising. Now, we've been working with these and finding that they have the same cardinality. What about the rational numbers? Would the rational numbers have the same cardinality? When working with the rationals, I have to set it up a little bit different. It takes a lot of space. One way to represent the rational numbers is to set it up like this. We start with 0 in the middle, and then we have 1, right above that to the positive 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I simply wrote it as 1 is 1 over 1, and 2 is 2 over 1, and 3 is 3 over 1. So there's an infinite number of natural numbers there that are in the rationals. Well, the rationals also include the negatives, so that's why below the 0, I have a minus 1, a minus 2, minus 3, written again as minus 1 over 1, minus 2 over 1, minus 3 over 1. There's an infinite number there. But the rationals include more than just the integers, even includes fractions. So, for example, if we go back to the 1, above the 1 over 1 is 1/2. And then above that's 1/3. And then above that would be 1/4, 1/5, 1/6, 1/7, and so on. Then you see above 2, what I did is keep the numerator the same and increase the denominator. So all of the fractions families are there. Above 2 over 1 is 2 over 2. Above that's 2 over 3. And then 2 over 4, 2 over 5, 2 over 6. And the same with the 3's. 3 over 1, 3 over 2, 3 over 3. And then next would be 3 over 4, and it continues. And then I did the same thing down below in the negative numbers, below 0 there. And we get, like, the last column there is minus 3 over 1, and then it's minus 3 over 2, minus 3 over 3, and then would be minus 3 over 4, and then minus 3 over 5. And it continues. And we realize, wow, just doing the natural numbers out, there's an infinite number of them, and then there's an infinite number of the negatives. And then doing the 1/2 fractions, well, there's an infinite number of fractions that have 2 as a denominator. And there's also an infinite number that have 3 as a denominator, the 1/3, and the same in the negatives. So we start to realize that when we look at the rationals, not only do we have 2 infinities that we're trying to fit inside of 1 infinity, we have an infinite number of infinities. These rows continue up infinitely, and to the left infinitely, and the right infinitely, and down infinitely. So there's an infinite number of infinities inside of the rational numbers. Well, surely that has to be bigger, have a greater cardinality than the natural numbers. It's just 1 infinity. After all, how in the world could you ever fit in an infinite number of infinities inside of just 1 infinity? Well, again, we'd have to show it or prove it. Well, one way to pictorially show this is to say, I'm going to pair off 0 of the rationals with 1 of the naturals. So that's my first pairing. Then I'm going to pair off one of, let's start with the naturals first, one of the natural numbers with 1 over 1 of the rationals. And then I'm going to pair 2 off with minus 1 over 1. And then I'm going to pair 3 off with 2 over 1, 4 with 2 over 2, 5 with 1/2, 6 with minus 2, 7 with minus 2 over 2, 8 with minus 1/2, and then 9, 10, 11, and then I just continue this kind of square spiral kind of shape that we're doing, and realize that I can pair a natural number with every number of the rationals if I keep making this spiral bigger and bigger and bigger. So that actually means that an infinite number of infinities fits inside of infinity. Infinity is so big that an infinite number of infinities can fit inside of it. That is humongous. And to get back to our question, with the rationals, then they have the same cardinality as the natural numbers. Wow. An infinite number of infinities fits inside of 1 infinity. That's big. Now, when we're working with this, with infinity, this lesson and the next lesson, one of the things we have to kind of keep in mind is it's helpful to look at Zeno's paradox to separate these things. When we're working with infinity, it really gets abstract. We have to kind of put aside, I'm kind of used to dealing in numbers. After all, the world is finite in size, so we're not used to dealing with infinity. Zeno came up with this paradox that shows kind of the difference between looking at things from a finite perspective and an infinite perspective. What Zeno did is he proposed a race. And the race would be between you as a runner and a turtle. Now, the turtle is no ordinary turtle, as you can see. He can stand up and run his hind legs. In fact, he's so fast that he can run exactly half as fast as you. Cannot run faster than you, can't run 3/4 the speed that you can. He can run exactly half the speed that you do. So if you have a race, who's going to win? Obviously you are. After all, you're faster than a turtle, right? Sure. Now, Zeno said, well, let's set up a race. And since it's not an interesting race if he runs half the speed that you are, let's make it interesting. Let's start you at the beginning. And to give him a chance, let's put the turtle halfway. Well, that means if you start slow, if you stumble, if you don't run your best, he's going to beat you, right? Or it's going to be a tie. Now, if you run your best, it'll be a tie. If you stumble or make an error, then he's going to win. So really, it's a challenge to you. Now, let's look at this race. If we just ran it and you ran a perfect race and he ran a perfect race, it would be a tie, right? Well, let's look at it from a different perspective. Let's look at the race in legs or portions of the race. So for the first portion of the race, for the first leg, let's look at this and say the first leg is the time it takes you to run to where the turtle was at the beginning of that leg of the race. So the time it takes you to run to where the turtle started. In that amount of time, he runs half the distance that you did, right? He runs half as fast as you. So he would run that far. Now, the second leg of the race, we're going to repeat this same process again. It's the amount of time, the second leg of the race, we look at it as the amount of time it takes you to run from where you are to where he was at the beginning of that leg. So the second leg of the race, you run to where he was. In that amount of time, he runs half the distance again. Now, in the third leg of the race, you run to where he was, and he runs half of that distance. And then we continue this. You run to where he was, half the distance that you did, and then you run to where he was, and he runs half the distance that you did. Now, if we continue this, who wins the race? Do you ever catch the turtle? Well, looking at it from this perspective, we say, oh, wow, there's a finite number of steps happening here. We get in and say, wow, I never catch the turtle, or you never catch the turtle. What? You mean you're not faster than a turtle? Especially a turtle that's running half the speed that you are? Well, now, in real life, we would know that if you both ran a perfect race, it would be a tie. And if we extended the finish line even just 1 meter, then you would win. You would pull ahead. Now, but if you look at it the way this is running, looking at each leg of the race, then you said, no, you never catch it. Now, in real life, of course, we know you would be a tie. And if it was any longer, you would win. So there's different ways to look at this. When you're looking at infinity, looking at it the way that we look at a race is looking at it through the eyes of infinity, very abstract. Even though it seems like you're always catching up to him, you do eventually catch him, and if the race was any longer, you would win. If you're looking at it from a finite perspective, then you say, I never catch the turtle. He's always ahead of me. So hopefully this can help if you're trying to figure out that ping pong ball conundrum and some other things. Remember, you have to it's like you reach in and scoop out your finite brain and put in your infinite brain. Think a little bit differently, and that'll help with this lesson and especially the next two that we run into. Now, the homework for this section, I do have, view the online video. Obviously, since you saw this, you just saw it. And then, of course, the pages, what I do kind of summarizes what's in the chapter and adds a little bit to hopefully help understanding. And then on pages 178 to 183, do those problems. I am going to ask that you take a photo of certain questions of those and email them to me. It's just a little bit easier if you email them to me. So I'm just going to ask that you do that instead of submitting them some other way. So if you have any questions, again, contact me by email and let me know.